In section 9.4, we're going to continue our discussion of hypothesis testing. We're going to talk about rare events. We're going to talk about our sample and then making a decision and reaching a conclusion. Just a reminder, our steps in hypothesis testing in general, what we're going to do is make a statement regarding the nature of the population. Remember, that's going to be in the form of our null hypothesis and our alternative hypothesis. Then we will collect evidence. We will be given sample data, and we will use that sample data to test the statements or to test the hypothesis, specifically the null hypothesis. And then number 3, we will analyze the data to assess the plausibility of our null hypothesis to see if we reject it or fail to reject it. If we reject it, then our evidence is in favor of the alternative hypothesis. If we fail to reject it, then we just do not have enough evidence to reject it. Example 9.4, in the California lottery, the odds of winning the first prize Super Lotto jackpot are 1 in 41,416,353. The odds of winning the Mega Millions is 1 in 302,575,350. Why would we consider winning either of these events unusual? Well, the probability of winning the Super Lotto, I'm just going to write it this way, is 1 out of 41,416,353. The probability of winning the Mega Millions, I'm going to abbreviate Mega Millions, is 1 out of 302,575,350. So if we just type those numbers into our calculator, so 1 divided by 41416,353, we get 2.41, and again, our probabilities cannot be bigger than 1, so that means we have to look for the times 10 to the negative 8, that e negative 8. That means 0.000000, 7 zeros, one more, and then 241. The chances of winning are extremely low. When we do this next one and we type in 1 divided by 302,575,350, we get 3.30 times 10 to the negative 9th. Again, your probability cannot be more than 1. So you got to look for that e negative 9, telling you it's scientific notation. That means we have 8 zeros, 1, 2, 3, 4, 5, 6, 7, 8. And then the 3. So again, remember our chances. If we had zeros in the first 4 spots, we said that's basically impossible. We might say 0.0001 just to say that it's not impossible, but it's almost impossible. And that's the case for both of these. These are just very, very unlikely to occur. And so that's why we would consider these events unusual events, because their probabilities are so low. In general, an unusual event is an event where the probability of that event occurring is less than 5% or 0.05. So notice these two examples that we've just done are significantly less than that 0.05. For our hypothesis testing, if we make an assumption regarding a population, which is our null hypothesis, and the sample statistics displays that it would be unusual for that assumption to be likely, then we have to assume that our assumption that we made about the population is not true. Even though we make the assumption, the data will tell us if there's sufficient evidence to support the assumption or to reject it. And again, remember our assumption that we make is the null hypothesis. Something equals something else. Note, when the results are found to be statistically significant, we reject the null hypothesis. So in other words, if our data tells us that the null hypothesis being true is unusual, that means the results are statistically significant and we reject the null hypothesis. The p-value is something we're going to be using quite a bit. We're going to get this value most of the time from our calculators. The p-value is the probability that if the null hypothesis is true, the results from another randomly selected sample will be as extreme or more extreme as the results obtained from the given sample. So more technically, if the probability of making a type 1 error, remember we said that was alpha, that's the stuff on the outsides, is more than the p-value, then this is statistically significant and we reject the null hypothesis. So again, the idea, if we want to just get a picture, and this is not always the picture, but this is kind of the idea that we said in class the other day. If your alpha is out here, this would be half of it, this would be the other half. But anyway, if your p-value, let's say alpha in this case is 0.01. If your p-value is less than that, so if alpha is more than p, let's say 0.007. So if alpha is more than p, that means the probability of that sample looking the way it does when our assumption is true, or when we make our assumption in the null hypothesis, that is so low that we are forced to, because this is higher, we're forced to reject our null hypothesis. And that p-value being out here means we're way out here, further out than our middle area there. Example 9.5. A normal distribution has a standard deviation of 1, and we want to verify a claim that the mean is greater than 12. A sample of 36 is taken with a sample mean of 12.5. Draw a graph that shows the p-value. So in our case, again, we want to kind of think about our assumption that we're making. Our null hypothesis would be that the mean value is equal to 12, because we have to state this as an equality. So we want to verify a claim. The claim is that the mean is greater than 12, but the null hypothesis would be that the mean is equal to 12. The alternative hypothesis would be that the mean is greater than 12. Okay, so when we look at this, notice that we are looking at a standard deviation of 1. It's a normal distribution. A sample size of 36 is taken with a sample mean of 12.5. Okay, so here's our 1, here's our 12 for the mean. So let's label that as 12. Now we do have to be a little bit careful because our standard deviation, remember how we do standard deviation of a sample mean, we take the standard deviation that's given to us and divide by the square root of n, which in this case is the square root of 36, which would be 1/6, or as a decimal, that's approximately 0.16. So that means going in a positive direction, this would be, for our next spot over, 12.16, that'd be 1 standard deviation. 12.32 would be 2 standard deviations. 12.4, it actually rounds up to end up being 4.9. I think this one actually rounds up to be 3.3 also, because 1/6 is not exactly 0.16. It's actually probably, now that I think about it, it's closer to 0.17. So we should have maybe done that. Okay, but this is the general idea. And when we look at that, notice that 12.5, what we got a sample mean of, is way out here, actually beyond this. And if this is a normal distribution, we can use our empirical rule here. We know that 1, 2, 3 standard deviations over, on the outside of that is only 0.15%, and that 0.15% means our probability is actually, of the mean being 12.5, the probability of that is actually going to be less than that 0.15% or 0.0015. So that is, again, a very unlikely event. To draw a picture of it, it's this tiny region over here, which is very small, that we have as far as the p-value, the probability. So that would be a very unusual event. We're not going to do these typically drawing a picture. We're going to do the math, and we're going to use the calculator to help us out to do this. But with this information, we would say, yeah, that's a very unusual event. We would have to reject the null hypothesis that says the mean is actually equal to 12, and therefore we would tend to accept the claim that the mean is actually greater than 12. So looking at this information, notice we've got the null hypothesis identified, we have the alternative hypothesis identified, and the actual p-value ends up being 0.0013, which we knew it was less than 0.15 because it was more than 3 standard deviations away. And so that is just, again, verifying that we would reject the null hypothesis. For example 9.6, we're going to be talking about the decision and the conclusion. It's a Boy genetics lab claims that their procedures improve the chances of a boy being born. The results for a test of a single population proportion are as follows. The null hypothesis would be that the chances of a boy being born are 50%. I mean, that's just kind of normal. You're going to get a boy or a girl, the chances are pretty much 50-50. The alternative hypothesis, according to the It's a Boy genetics lab, is they're saying that whatever they do in their treatments, that makes the chances of having a boy, or the proportion of boys being born, is higher than, greater than 50% or 0.5. We are going to test this at an alpha equals 0.01 significance level. And let's see, the p-value that we are given is 0.025. So we didn't do any math here. They're giving us all these values. Here's the 0.025 for the p-value that they gave us. And we are just supposed to compare these. And in this case, alpha is less than p. 0.01 is less than 0.025. If you need to add another 0 to compare, you're looking at 10 thousandths compared to 25 thousandths when we compare these two. So alpha is less than p. So this is not statistically significant. And if it is not statistically significant, we fail to reject the null hypothesis. Okay, the conclusion in terms of this context would be, we would say, even with their treatments, whatever they're doing, we cannot reject the proportion being 0.5 according to what we have gathered in our sample. And again, we didn't do any of the math. They gave us this information. But when alpha is less than p, we fail to reject the null hypothesis. And in that case, that means we don't have enough evidence to support the It's a Boy genetics lab's claim that they can make it more likely to that a boy will be born. The way we would write that is, there is not enough evidence to support the claim and then you just go on and state the claim, which is their claim that their procedures improve the chances of a boy being born. I can't fit that all on the bottom of my screen, but that would be the claim that there's not enough evidence to support. Example 9.7. The administrator at a local hospital states that on weekends, the average wait time for emergency room visits is 10 minutes. Based on discussions on the length of wait time to be seen in the ER over a weekend, an employee disputes the administrator's claim. The employee decides to test his hypothesis. Over the course of a few weekends, the employee records the wait time for 40 randomly selected patients. The average wait time for these 40 patients is 11 minutes, with a standard deviation of 3 minutes. Does the employee have enough evidence to support his claim that the average ER wait time exceeds 10 minutes? He tests at a 5% level of significance. If the null hypothesis is not rejected, then what is the employee's conclusion? So now I have a little bit more space to write. it says the average wait time for the emergency room visits is 10 minutes. That is the null hypothesis. That is what the administrator claims, is that the average, mu, is equal to 10. The average wait time for 40 patients is 11 minutes with a standard deviation of 3 minutes. So our null hypothesis, according to our worker there, is that the mean is actually greater than 10 because he's seeing a longer wait time. So, and again, here's where we get that. Does the employee have enough evidence to support his claim that the average ER wait time is or exceeds 10 minutes? So that's greater than. And one thing we might want to note is this is the claim of the employee. Then if we go through this information, there were 40 patients, so n is going to equal 40. 11 minutes was the average wait time for those 40 patients, so that's x bar is 11 minutes. The standard deviation of those 40 patients was 3 minutes, so that's going to be S is 3. Let's see, what else do we have? Oh, he tests at a 0.5 significance level. Well, that means alpha is 0.05. 5% turns into 0.05. So what we're going to do now is we're going to take this information, we're going to plug it into our calculators, and here's how we do this. Notice we do not have the standard deviation of the population. We have the standard deviation of the sample. Where is it? So here's our sample information. We have the standard deviation of the sample. So this is going to be a t-test. It's very important to remember which test you're using at what time. So we're going to go to stat and over to tests, and we're actually going to just choose number 2, a t-test. And we're going to enter in our statistics that we were given. So the null hypothesis, mu sub 0, is 10. X bar is the 11 down there. S of x, which is the sample standard deviation, is 3. N, the sample size, is 40. And then here's where we have mu is what compared to mu sub 0. So in other words, the mu of the sample is what compared to the standard deviation, or the original, the null hypothesis, and we're saying that mu is greater than that 10. Okay, notice that's right here. We're testing that claim that mu is greater than 10. So we're going to go to that one and hit enter and go down to calculate and hit enter. And notice we get these values. So we're testing that mu is greater than 10. The t value, if you cared about it, is 2.108. Here's the one that we're going to focus on. P is equal to 0.0207. So our result is P is equal to 0.0207. And then it lists the other information that we already typed in. So this is the key. We're going to compare P to alpha. And in this case, alpha is greater than P. So when alpha is greater than P, we reject the null hypothesis. And so our answer in this case would be, we would reject H sub 0 because the chances of P happening are less than our alpha value. Okay, and then as a conclusion statement here, now let's go back. If he tests at a 5% significance level, he actually does have enough information, enough evidence to reject the null hypothesis. We're going to make this statement and then we'll go back and answer that other question. So our final statement would be, there is enough evidence to support the claim. And notice our claim was right here in the alternative hypothesis that the wait time is greater than 10 minutes. Okay, so that would be our conclusion in a normal situation. Now, in this particular question, they specifically ask if the null hypothesis is not rejected, what is the employee's conclusion? Well, if the null hypothesis is not rejected, their conclusion would be just the opposite. There is not enough evidence to support their claim that that the average wait time is greater than 10 minutes. But in our case, they did come up with enough evidence. So anyway, we get both sides of that. If P would have been greater than 0.05, then it would have been that case that they're asking about. But since P was less than 0.5, we are going to reject the null hypothesis, and therefore there is enough information to support our claim. So I don't know that any of them actually get into the math part of what we did at the end there yet. I think that's going to be mostly in the next homework section. But for this one, you've got 5 graded problems. Again, make sure you try those. And if you have questions, please don't be afraid to ask.